Hello everybody, I am Miguel Saavedra Chimal and I am going to present the project design of estimators based on a reticular scheme. I have done this for practices in the profession too for UDLAP at the Instituto Nacional de Astrofísica, Óptica y Electrónica INAOE. Well, I have three main contents: introduction, development, and conclusion, and I am going to start with the introduction. Well, this project consists in making a literature review and mathematical analysis in order to understand everything about the Fourier coefficients, and this is going to be based on the derivatives and the semi-sinusoidal signals. Well, what is our objective? To understand the harmonic estimation method through the reticular scheme of the derivative calculation of a semi-sinusoidal signal. How? By making a careful analysis. Why? To determine the harmonics with a small number of samples. This is very important. We need to obtain this method with a small number of samples. This is our main goal. And how are we going to measure this? Through a simulation and MATLAB. Well, our goal is to make a report with an understandable explanation of this method and a description of these clear advances by making this for a small number of samples. Well, I'm going to start with the development. The methodology used was to make a bibliographic review, then the development of these numerical derivatives that we are looking for, and the solution of these equation systems, then making some tests by some stimulus calculation in semi-sinusoidal signals. Well, then we're going to analyze the results, and after that we have to write a report. Well, taking as a premise that every signal can be expressed, because of Fourier, as an infinite sum of sine and cosine function. Well, this is expressed like this. We have a principal component here and two harmonic distortions, one with sinus and one with cosinus. Well, what we need to obtain are the coefficients here, A1, AN, BM. So we're going to use the analysis of Rinaldi, and well, I'm going to explain this. Rinaldi takes one simple sinus like this function. He make the division of the second derivative and itself, and he obtains the frequency just by making some mathematical analysis. Well, if we now calculate something like this, we can obtain the amplitude, but as we can see, we have here just mathematical analysis and the frequency. So we have to replace this frequency here and make some analysis, and we have already the amplitude. So as we can see, it is possible to obtain this amplitude coefficient by having just a simple sinus. So what we have to do is to develop a method capable of eliminating these harmonics. So we are going to explain this at the contributions. So if the original signal is defined as we have already said, the first terms define a principal component and the other two the harmonic association. And well, what we can do is to have the second derivative, and we observe that here we have a term that it doesn't help anymore. It is the frequency, so we have to normalize the frequency, assigning 1 to this principal component. And well, after that we have to add the main function with its second derivative, and we obtain an equation with no corresponding frequency to the principal component. So we can obtain this. We can do this again in order to obtain an equation with no harmonic of the second, with no component of the second harmonic. In order to obtain the k equation, we have to apply this here, and well, it is pretty easier if we see this in an example. If we have this as main function, like our principal component and two harmonics, two sinus harmonics, Well, we have to apply the method, and we're going to obtain a V2 where the first coefficient is going to be eliminated, and we only have the second and the third. And if we apply this again, we are going to eliminate this second coefficient and only have this third coefficient. So now that we have this, we can already apply the analysis of linearity in order to obtain the amplitude. So once we have the amplitude of A3, we have to obtain the another coefficients. So we need a regression, and this is going to be made like this. Well, but for the last component, named mth component, and for the principal component, it's going to be a little bit different. Why? Because as we can see, here we have the sum of k, which is m plus 1 until m, but we have no sum here because n plus 1 is already an m, so this is going to be eliminated, and the same applies or something similar in this principal component, because here at the product we need to make the product from I where is 1 until n minus 1, but n minus 1 is going to be 0, so it doesn't have any sense. So this is going to be eliminated, and we only have this here. So we have to apply this regression iteratively until the main component is recovered. And well, we have all the coefficients, and we can make a whole reconstructions like this. And well, it is very important to say that this is the whole method, but applying this in MATLAB, it is going to take a lot of computation time. So we're going to need the formulas described in Lara in order to use this fundamental theorem of calculus and to make quicker this process. So this fundamental calculus says that the derivative of a function is where it tends to 0, and this formula that we all know, and this can be just like expressed like this. And if we want to take the second derivative, we have to make something like this, and we can replace here this equation here, we replace it here, and this equation here, we replace it here. So we can obtain this equation, this whole equation of the second derivative, and this is going to be very, very quickly. So if we take into account that our function is a sinus, we are going to have something like this, okay? So the results, well, we can have an example. Our method was tested in this equation, like A1 is going to be 1, A2 is going to be 0.2, and A3 is going to be 0.15. So what we have to apply, we are going to know that we have 3 harmonics. With filters, we can reduce this to 3 harmonics. And when we have these 3 harmonics, we apply our method, we apply to V2, we have no longer A1, we apply to V3, we have no longer A1 or A2, and here we can determine A3. After determining A3, we have to make this regression in order to obtain A2 and A1, and the results were the following. Well, A3, as we were expecting, we obtained 1, and this is a result of the indeterminate, but here we have a pretty good result of 1. A2, as we have expected, is near to 0.2, and here A3, 0.15, just like we have expected. So if we reconstruct these coefficients, this whole equation, we're going to have this comparison. As we can see, it is difficult to see a difference, but here are the 2 equations, the original and the estimated. So we're going to make some sum, and as we can see, it is not exact, but it is pretty near to our results. So we can say that our system, our method worked. As a conclusion, well, I have acquired many new knowledge because this subject was totally unknown for me, and now I know how to estimate these Fourier coefficients. And well, we we know now different methods for these estimating coefficients and the use of derivatives through fundamental calculation thanks to Rinaldi. Well, we also know that we can graph these derivatives in MATLAB, and we know the importance of this in in power quality. I also was able to write a scientific article, and well, we are waiting for approval now. Well, this application is limited to the need of derivatives, so we need only continuous signals. But it is very useful for certain applications like the power factor measurements. It generates an efficient method that needs few samples. That was our goal. And well, the companies can ensure that the expected signals are those delivered, so the devices connected would not be damaged and the cost is going to be reduced. I want to thank my tutor, Dr. Alejandro Diaz Sanchez, and well, these were my references. Thank you.